And we are recording. Okay, so let me hand over the presentation to group 4 to present their modified, that's an acronym, Microbioreactor Innator.
So without further ado, as Dr. Trump said, this is group 4. Welcome to our final presentation, and we'll just quickly go around the room and introduce ourselves.
My name is Francisco Di Capua. Anyone?
My name is Daniel Hasbun.
I'm Francesca Lopez.
I'm
My
Danielle.
name's Ashley Maple. Oh, Larry Myers. Ashley Maple and Danielle Myers.
I'm Dara Parada.
And I'm Roxana Storms.
And we'll move on to the actual presentation now, assuming it wants to lead this slide. There we go. So quick meeting agenda before we get started. We'll do a product overview, and then we'll delve into the rest of the project where we'll talk about our Hedgehog concept, some key features and exploded views and drawing views, go through an analysis of subsystem designs, talk about our technology readiness levels, TRLs, simplified cost table, why modified should be selected for MEC 3, and a quick conclusion slide. So we'll start off with product overview. As Dr. Traum was saying, yes, modified is an acronym, and it stands for Microbioreactor with Optical Density Integrated with Fluorescent Intensity and Experimental Data Collection. Big mouthful, we know, but we wanted to simplify that, and we made an acronym that we liked and kind of worked backwards from there. So, functionality of our product: modified transfers fluids between well plates and conical tubes using a pipette-style dispensing system, which we will get into later. And well plates are transported between 2 different subsystems using a claw mechanism. The microbiological MS subsystem cultures bacteria, can take temperature, controls the gases, and the ECD subsystem measures the OD and FI in the well plates and the conical tubes. Then culture conditions are transmitted to a laboratory remote computer rather than controlled on the physical device itself. And we have a digital readout, DRO, on the side of the device that you can kind of move around, and you can see the displays of all the readings on the screen. And we will get into all of these points later in the presentation. So our device overall footprint, we have some dimensions there in either metric or English units, and we can see it's approximately 1250 by 1474 by 780 millimeters cubed. And with that, I will hand it over to Roxana to talk about our Hedgehog concept and some key features.
So the concept of our design is customizability. We know that in a lab, there are so many different experiments that you could do. You could test E. coli, you could study a new vaccine, you could study any kind of new culture that could exist in the world, and there are millions of different bacteria that exist with individual needs. As a result, we wanted to create a design that would be able to be customizable by the researcher. So first of all, our device is controlled with a laboratory computer. A lot of different devices are controlled with hardware built into the system, but our design runs on software that will allow the researcher to easily access the results and also make adjustments. They could control the temperature inside the microbioreactor. They could control the shaking patterns from the computer. They could program the direction that their claw will move within the microbioreactor, and it allows for more customizability inside the microbioreactor. Next, our frame is made of 80/20 that will allow for future modifications. The researcher would be able to add extra accessories on top of the microbioreactor, for example, a camera or a different tool a sensor that would go inside the microbioreactor, or if they need to adjust the size or build on another piece of machinery to the microbioreactor. We also have a versatile claw and liquid handling subsystem that navigates throughout the microbioreactor with our XY axis that will transport both fluid and well plates. And as I said before, they can control and program how that will move across the whole entire cross-section of the microbioreactor. Also, our microbiological sustainability subsystem has variable temperatures, atmospheric gases, shaking patterns, and unique culturing environments. And as I said, there are so many microbiological systems out there, and each of those microbes has its own needs. So this will allow the researcher to make adjustments based on the culture's needs. So next, I'm going to talk about some of our key design points in our design. First of all, we have our general build. So our general build, as you can see, has an 80/20 frame structure, and it also is equipped with 2 emergency stop buttons on either side to allow for the customer to shut off the machine at any moment in time. We didn't want to, we started out with just one emergency stop button, but we included two so that way it would be more convenient in case there was emergency. Second, we have our adjustable digital readout on the left-hand side of the general build, which will display the results or display what the progress of the experiment is, or display if there is an error of sorts. And we also have an oven-style door that will allow the researcher to easily insert the well plates filled with the microbiological subsystems.
And with that, we will pass it on to Daniela Myers. Yeah, we'll pass it on to Danielle Myers to talk about the versatile claw.
Hi, so the versatile claw is basically, we'll be transporting the well plates from one point to another. And it's made with a sheet metal, it's stainless steel 16 gauge sheet metal, and that's going to house two NEMA motors that control lead screws, and those lead screws will spin so that those arms there will open and close so that it could pick up the well. It's going to be lined with a gripper so that it can hold on and keep a grip on the well. On the bottom, there's a mount there that is attached to a guide rod, and there's Teflon bushing so that the metals don't interact with each other. And then the top is located, or it's attached to a lead screw so that it doesn't spin and it keeps its structure. On the top, there's another stepper motor, and that allows the casing to swivel so that it could move better. And then that large lead screw on the top is what controls the Z-axis motion. And it's not shown, it's in the main assembly. There is going to be a stepper motor connected to that lead screw, and that's going to be on the XY axis on the top of the frame. And something that's a good, cool feature about this is that it can pick up well plates and it can pick up Petri dishes as well, if that's something that Modified may look into the feature and improving. So on to Daniel, he can talk about the fluid handling system.
Here we have our liquid handling subsystem. The primary purpose of the liquid handling subsystem is to extract liquid from the well plate or from the test tube and deposit it into any of our other subsystems for testing purposes, such as the optical density and the fluorescent intensity. And to do that, it uses two stepper motors and two lead screws for vertical motion. You have the one lead screw in the left support structure that actually moves the liquid handling subsystem up and down along the interior of our design. And then we have another lead screw and motor actually inside the little pipette burette assembly that actually moves a plunger up and down, which is going to be used to extract the liquid and to propel it down to wherever it is that you need to do. It is the casing of the actual liquid handling subsystem is made out of hard polystyrene, and then the support structure around it is made of aluminum. And that's about it.
So with that, I will hand it over to Francisco, who will talk about our microbiological sustainability subsystem.
Almost forgot to mute myself, excuse me. Thank you very much. This is our microbiological sustainability subsystem. Its main purpose, of course, is to provide a conditioned, enclosed environment for the microbes being researched. And these conditions can be preset by the researcher, by the user, and regulated through closed loop control. The frame is made of extruded polystyrene. The door, which slides up and down to actually enclose the environment, is made of clear acrylic. And the temperature is regulated using the Peltier modules, two of them. They're attached to the wall, as you can see there. These Peltier modules consist of, each of them consists of a plate, two heat sinks, one on the inside, one on the outside, and two fans, again, one on the inside, one on the outside. And so we have two of those modules. The temperature is also regulated using a temperature sensor located directly under, right there, yeah, thank you, under the modules. That gets redirected to a controller, and temperature is regulated in that way. As for the gas mixtures, the gas mixture is regulated by a series of mass flow controllers. Each mass flow controller is connected to its respective canister via plastic tubing, and it's directed towards the environment as well. Each mass flow controller, so one is connected to oxygen, another one regulates nitrogen, another carbon dioxide, another methane, and the fifth hydrogen. The fan, there's a centrifugal fan attached to the top of the system, which is meant to expel any excess gases out of the system, out of the environment and out of the general system. And lastly, the last main feature of this environment is the incorporated off-the-shelf shaker. You see that sits at the base of the system and contains a well plate just for visualization or size visualization. This off-the-shelf shaker can perform linear, orbital, and double orbital shaking patterns. And that does it for the microbiological sustainability subsystem. With that, I believe I will hand it off back to Francesca.
Yep, and from here we will be talking about the analysis of our subsystems design. So very quickly, this is the complete customer needs map tied to our quantified metrics, how they relate to all of our subsystems, and more analyses from there. Currently, I just want you all to focus on the left-hand side, which is the complete list of all the customer needs, and then notice how each of our subsystems in the middle, the 6 bubbles in the middle, are all directly tied in one way or another to all of the customer needs. So this graphic was just to prove and demonstrate how our design meets every single customer need. So from there, we'll kind of delve into the more key customer needs that we thought were like the most important ones each subsystem should tackle. So for general build, that's the exterior surface is less than or equal to 55 degrees Celsius, and it will not go over that temperature, which will be controlled by the MS subsystem and keeping that unit within check. The general build can also be assembled and disassembled with minimal know-how from the 80/20 frame. And it's easily accessible to a user of average height and build. And I myself, as a person of beneath average height and build, will also be able to access our device. So that was a nice little feature. We didn't make it too big. So moving on to the holding capabilities. Subsystem, our device can accommodate all 6 required well plate sizes and all 2 required conical tube sizes. The liquid handling subsystem can automatically add and remove liquid from each well plate and conical tube, and it achieves the required dispensing rate, and those values are found below, and it also deposits the correct amount of fluid volume in the correct increments. That range is also found for your reference. Moving on to the other subsystems, our user interface includes a failsafe and has a visual indicator easily seen by the user. That's our DRO that is movable, so you can either have it attached to the wall or have it swing around so it faces you, the user. And we also have controlled parameters that can be modified through our remote computer. The environment condition detection subsystem can obviously read OD and FI measurements. It has the correct light intensity and wavelength, and it uses monochromators to measure OD and FI. The microbiological sustainability subsystem uniformly heats the well plates and the conical tubes. It can culture at the required temperature, which range is again found below, and it includes gas controllers that can appropriately regulate the 5 required gases. And as Francisco said, it can conduct all 3 independent shaking patterns. So from there, I will hand it over to Ashley, who will talk about our TRLs.
So just a quick overview. I'm sure by now, as with the last presentation, you are all familiar with TRLs, but technology readiness levels were developed by NASA, and they're used to quantify the risk when developing technologies. For MEC2, we focus more on the design, and that correlates best to the first 3 TRLs, which are our subsystem is within those. In Mech 3, when you're actually prototyping and building, then you will enter the lower ones of like 4 and 5. So, 5 of our subsystems are in TRL3, which means they have had analytical calculations done to them. And our user interface we felt was at a TRL2 because as we have the concept for how we want the controls and the actual like code and user interface to look, but we have not implemented these yet. And once that has been done and tested, it will be a TRL3 as well. Next slide, we have our cost table. And these are the expected costs we feel will occur when building the device. The majority of our costs come from off-the-shelf parts as monochromatometers and sensors are very expensive, bringing our OTS budget to just under $9,000. For the components we will be manufacturing, we calculate the price for the raw materials to be $643. Using the tables and multipliers provided to us in class, the manufacturing labor and assembly costs were found to be $661 and $340 respectively, putting us at a total slightly over budget at $10,617.
So from there, I will pass it on to Daniel, who will talk about why our design should be selected for Mech 3.
Thank you. So why choose modified? Well, the modified is a highly customizable autonomous bioreactor. Specifically, our biggest feature in terms of our customizability is our external program, which is able to modify the parameters inside the machine. It's able to modify testing parameters. You're also able to do multiple fluids within the machine in terms of the fluids like within the well plates. Our design requires the user, the scientist, to actually put in their own liquids into the well plates before you actually run the machine. So that way you're able to test any sort of liquid, any sort of cell culture that you want. And we don't have a set limit of like liquids that the machine is able to produce. And you don't have to fear about cross-contamination when using the liquid handling subsystem to pick up the liquid and to dispense it elsewhere within the device, because the pipettes are removable. There is a little container within our build that is able to deposit the used pipette tips, and then the liquid handling system is able to get more pipette tips from a little pipette tray within the device. Our versatile claw is also compatible with virtually all of the standardized well plates and an assortment of the test tube dimensions. So you get the ability to test within a wide range of laboratory plates and tubes and whatnot. Also, another key feature is our modularity of the design. So all of our subsystems are compartmentalized, basically, which means that it's easy for construction within EML4502, and the various use of all the off-the-shelf parts for the essential functions of our machine lowers the overall manufacturing time.
Thank you, Daniel. And with that, I will pass it on to Dada, who will talk about our key takeaways.
Yeah, so to summarize our design, the basis of our team's Hedgehog concept is customizability, as we think it will aid the user in their experience using our design. Some of the key features of our design were the simple and inexpensive 80/20 frame, the claw to autonomously transport well plates, the autonomous liquid handling system, and the independent filtering environment. The next step for our team is to create a prototype to test the functionality of our design in a lab setting. So we'd like to thank you for listening, and we welcome any of your questions on our design.
Okay. Wow, right on time. Perfect. So, any questions from our panelists?
So I have a few. Could you guys go back to your enclosure where you have the orbital shaker in?
Yeah.
The slide.
Bear with me while I travel.
So A common theme that at least I've seen today through the presentations today and yesterday is heating and cooling times being a big issue. So did you guys do any hand counts to figure out how long it's going to take to heat and cool that chamber?
Yes, we did. We solved for a time constant, and from there, we would evaluate how long it would take to heat and cool. The time constant itself was approximately 330 minutes. So that's going to put our actual heating and cooling at somewhere much larger than that. So I hope that, yeah.
And then, so essentially, also the orbital shaker that you guys are buying off the shelf, how do you guys plan on controlling it? Because I'm assuming if it's off the shelf, it's going to have some sort of hand controls on it, because typically that's how you would use in the laboratory setting. So how are you guys planning on adapting that to be able to be automated with your control system?
Good question. So ideally, the goal would be to add a control, or to rewire it and add a control system that would attach itself to the remote computer and then be able to control it from there, as the remote computer would be able to control the majority of, well, not the majority, all of the device.
Have you guys looked into if it's possible to rewire it, or if it's like an integrated circuit board, or is it?
To be honest, that's not really something we considered, but we will look into that for future, I guess, preferences.
Also, while we're on the topic of the enclosure, is there a way to remove the gas, or is do you guys basically just lift the door and vent the gas inside the larger enclosure?
So we have 5, they're not depicted here because they were added to the overall CAD rather than to the subsystem. So that's our bad for not including it into the actual diagram. But behind these tubes, there will be 5 different mass controllers. And each of those, like there's 5 tubes, so those will be for each respective gas. And that'll control the ins and outs of it, as well as this exit tube over here. That'll be the exit way.
So I understand that you have the 5 tubes for each of the individual gases, but where do you vent the exhaust gas is my question.
So sorry, yeah, the exhaust gas is actually vented through that centrifugal fan.
To like an external waste bottle or into the container?
Mm-hmm.
Yes, to an external laboratory waste bottle. The gas coming in is through the mass flow controllers and the tubing. And then the excess gases are expelled through the using the centrifugal fan and unflow an excess.
So are you guys like assuming that the lab's going to have capabilities to pressurize the waste bottle, or are you guys containing the waste bottle? Okay. And then the last thing about this subsystem is there a motor to lift the door? I just couldn't tell because of the CAD.
Yes, there is. It is not shown here, but that's because it's attached to the general assembly. So yes, there is a motor. Okay.
Any concern with tolerancing in terms of manufacturing that door to get that door to slide nicely in the up and down the tracks? Because it looks, this is the way it is right now, it looks like you're kind of relying on the acrylic cut edges in your tracks.
So this is actually one of our tolerance loops, and we are currently in the process of doing that.
Okay.
Okay, any other questions?
So I have a few. So looking at this, and I realize the CAD can be a bit deceiving, but you said something about you being able to lift it and move it around and everything. So what's the weight on this?
That is something we have not calculated or looked into. One of the customer needs was that it be able to fit on top of a lab bench, which it does, but weight was never a requirement.
Well, if it has to fit on a lab bench, the lab bench should not fall under the weight, right? Like, I mean.
Yeah.
So
fair point.
It needs to be supported, and
yes,
we have to be careful as to how heavy these things are, right? So because that looks pretty heavy. Sorry, go ahead.
Oh, sorry, the frame is made of polystyrene, of extruded polystyrene, mostly. So and then an orbital shaker and 2 Peltier modules. I think the benchtop would be able to support the system just fine. on the fan as well.
Yes, and we didn't choose metals that were very dense. We chose like aluminum and other materials. So we think it shouldn't be an issue, but we can definitely look into it. Thanks for bringing that concern up.
Are you guys concerned at all about the 80-20 stiffness because of the fact that the entire frame is made out of 80-20? So when you bring it into the lab, it's going to have a tendency to move on you. Because if you remember from DML, I know Dr. Nemi's not here, he'd be loving this, but the 80-20 is great for temporary stuff, but it's very difficult to keep it rigid enough for a permanent structure because of the fact that the fasteners tend to loosen over time, which you're probably going to have when you move the structure into place. So do you guys have any like, did you guys do anything to mitigate that, or maybe explore alternative methods?
Alternative methods, no, but like any device, you need to routinely check in on it. So it's kind of like your car. You take it in for an oil change every 5,000 miles. So it's something similar to that, where you just maintain your device on a regular basis. So if that means tightening screws, that means tightening screws. But it will be assembled pretty toughly the first time around.
Yeah, additionally, we prioritized customizability, and we found that 80-20 was one of the most customizable materials out there. So yes, it may have some issues with the screws like you mentioned, but that is something that can be mitigated by routinely checking, like Francesca said.
So you're assuming the lab tech's going to have to go through and check all the fasteners once it shows up?
That's required of laboratory equipment in general. So we didn't feel like that would be a major.
Okay, no, so the counter to that is, the answer is no, that is not. That is emphatically not true.
Oh.
Okay.
I was going to say, Amor, isn't that why you have all those grad students? Aren't they supposed to go around and just tighten screws all day? That's what I did for 6 years.
Just my big concern is you're going to have to disassemble half of the outer panels and everything and check every single fastener. When ideally, if you work in a bio lab, you're not checking everything for mechanical integrity. The machine's here. I spent 10 grand on the machine. I want the machine to work. I don't want to have to fidget with an Allen key for 4 hours.
And that's an understandable statement. That's just one of the, oversights and downsides of having mechanical engineers design something that belongs in a biolab. We didn't really think of that because we're coming from a mechanical perspective where we routinely go in and check our devices and make sure everything's still properly tightened.
So you don't happen to think this is a mechanical device?
On some terms, yes. So I guess the build of it, yes, it is a mechanical device.
I see. Did you actually do the heat transfer and the modeling and all of that for the environment? You don't happen to think that that's also a mechanical engineering problem?
Yes, it is.
Okay, what about the construction and the structure? Do you happen to think that that is a mechanical engineering problem?
Again, yes.
Okay.
But it was more the functionality of the device rather than the build of it. Is what I was trying.
So does that mean that when you work for industry or a company, you're going to be very selective about the kinds of projects that you put on, and you're going to say that I don't believe in building this as a mechanical engineer? Is that true?
Absolutely not. We've completed this entire project, so that's not true. I'm just saying we don't have the biological standpoint. So we as mechanical engineers are used to routinely checking our products versus just assuming that they're meant to sit there pretty for the entirety of their life.
So I, as a mechanical engineer, by the way, happen to think that mechanical engineers need to know a lot of interdisciplinary and multidisciplinary things. I believe in lifelong learning. Hopefully you do too.
Yes, 100%.
Okay, so then consider this a learning experience, I think.
Absolutely. Oh, it 100% has been. This has been quite the experience to learn about all of the different types of bioreactors that exist and having to model our own. It's just not something that we were, I guess, used to. A little bit outside the comfort zone, that's all.
Well, that's the point, right?
Mm-hmm.
Can you guys go to the XY gantry slide where you guys should depict the XY motion with the the very first one, I think it was?
Yeah, I was gonna say that's probably our first slide.
Are you guys at all concerned about the large cantilever beam that you guys have in terms of both the one for the syringe and then the one that picks up the well plates that you're creating at the top point? Because you're basically, you're essentially, just making a giant cantilever beam that you're swinging back and forth on your gantry as you move it, because you're going to create a lot of momentum in order to have to stop it accurately. So I'm just wondering if you guys did like any kinematic analysis or what was your thought process in terms of doing that?
So in terms of kinematic analyses, we have not done those, but we can consider adding those for our FDR report. But I will hand it over to our lead design, Daniela, to talk about her thought process for, well, actually, no, this was Roxy. I apologize. Roxy did the XY track.
I'm sorry, could you please restate your question?
So I'm just curious how you guys are handling, because if you look at the both the syringe as well as the arm that picks up the dish, the Petri dishes, you essentially have a really long cantilever beam attached to your anchor point that's writing on your track or your slide. I'm not sure how it's attached.
Oh,
it's
yes.
hard to see. I'm just wondering if you guys did any like hand counts or anything, or figured out, hey, yes, the system's going to be able to account for the momentum that we're going to be creating, and then the massive rotational force you're going to have in terms of stopping a load where your mass is at the bottom.
So actually, it is in the cantilever beam. It actually runs on a track of 80/20. So,
but you're hanging something down from the track, aren't you?
You're talking about the claw, correct?
Yes.
Oh, yes. Oh, I understand. Yes. Okay, I thought you were talking about the XY transport. Yes, it is running. We didn't analyze that, but we didn't think it would be an issue based on the materials we selected. The carriage that it runs on is proportionally a lot larger than the liquid handling in the claw, so we don't think that a lot of large stresses will be created there. And it's attached pretty strongly in that area as well, so we don't think that will be an issue.
Does it ride like on a linear rail, or how do you guys constrain the motion on it so it's only
there's a track that is attached to the carriage of the liquid handling in the claw, so it'll slide along inside the grooves of the 80/20.
Okay, so like using the ones that are like the ones in DML, the tracks in DML.
No, we found some off of the 80/20 website that was compatible with 80/20.
Okay. Are you guys concerned about slop in the system? If you guys just like a big thing becomes, which is typically why you either switch to using linear rails or you use typically the wheels, especially in 3D printers, is you typically run into the issue of you run into slop in your system, and that's why they tend to use the grooved wheels so that you can pinch either the extrusion, or you're using a linear rail system in which the rail is on the carriage rides on the rail.
No, we're not concerned about that. The univarying pad that we selected for this is used commonly. It's actually used in the off-the-shelf part that we use for the environmental condition detection system. And it was modeled off of the XY axis traveling system that's in there. So we aren't concerned about that.
Okay.
I might have missed this. Did you guys do your TRL analysis of subsystems? Was that in there? It was. Okay.
Yes, it was. It's right. Bear with me as I.
Oh, there it was. Okay.
Yep.
Great. A lot of other teams did it like system by system. You guys had it all on one slide. I was probably too mesmerized by those particles going past.
I paused them just for you this time.
Thank you. I need that. I once had a student in a teacher evaluation say, Trom is great, but I'm worried that he's going to die because he's going to chase a shiny ball into the street and get hit by a bus. And that comment actually ended up in the letter that my dean wrote to evaluate me. That Trom is scatterbrained. So anyway, yeah, having those little things run by is like, ooh, shiny things.
They are mesmerizing. I will give you that.
All right. Do we have any other questions from the panel? Okay, seeing none. Hey, we're right back on time. It's 4:46, so 1 minute over. Okay, well we'll stop recording there then, and